Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, hello and welcome to the Trustworthy AI webinar. My name is Bolei Zhou from Technical University in Berlin. And I'm very happy to introduce the speaker of today, Bolei Zhou. Bolei is an assistant professor in the computer science department at the University of California, Los Angeles, UCLA. He did his PhD at MIT in 2018, where he developed a number of widely used interpretation methods, such as CAM and network dissection, as well as was working on a bunch of computer vision benchmark, such as Placers or AD20K. Yeah, so Bolei interest lies at the intersection of computer vision and machine autonomy, especially focusing on enabling interpretable and trustworthy human-AI interaction. So it's my pleasure, Bolei, and I very much look forward to your talk. So the floor is yours.
All right, so thanks for the kind introduction, Dr. Samick. Thank you for joining me today online. So today I would like to share with you some of the research on human-AI interaction in computer vision and machine autonomy. So I'm trained as a computer vision scientist, but after I built my own lab, so we have done many work in this embodied AI. So today I would like to share with you also some of the work in this machine autonomy site. So there are many exciting applications of AI and computer vision, from self-driving to whole robots to healthcare applications. So those applications are very exciting, but in each application, there are always two parties, right? So in self-driving, so you can see we have one party, the driver, human driver. Another one is this autopilot AI program. Also in whole robots, we have the elder people, and we also have the robots. And also in the healthcare applications, such as medical AI, we have the physician, as well as medical AIs. So in each application, there are always the interaction between human and AI. So for all those real-world applications, so we really need to build this trustworthy interactions and relations between humans and AI. So that's what I care about. How can we build this reliable and trustworthy interactions between human and AI, algorithm and machines. Also, AI is achieving human level and even superhuman performance on a range of tasks. For example, we have the ResNet that achieve the human level recognition for image classification. We also have the neural network that train to generate image. Then we have the StyleGAN that can generate realistic fake images. Also, this neural network AlphaGo is playing the strategic games, such as the game of Go that outperform the best Go players in the world. And also the machines is automating this vehicles. We have this autonomous drivings that can deliver human passengers to the destinations. So those results are very impressive. And also we have this title superhuman performers. So we are really impressed by the performance of AI models. Then there is another narrative of such a superhuman AI on overtaking humans. So people worry about these machines will take over jobs and to replace humans. So we have this automation in factories, then not all workers have been replaced. Also in the future, we have autonomous driving, then the taxi drivers will be replaced. Also, we have a lot of this sci-fi movies talking about AI threatening mankind, right? So these are very frightening futures, right? So we have this all the crazy machines and AI that will overtake human. So this is a narrative on the competition between human and AI. But here I will argue that humans and AI shouldn't be adversarial or competitors. We can change our relations. So the relations could become more like a collaborative relations. So really, what the AI should do is to augment human capabilities and offer more possibilities. So we can think about the AI technology as some our existing inventions, such as airplane, right? So we have the airplane that can deliver us to destination more efficiently and faster. We also invented the telescope that can help us observe the outer space much easier. So I really think this AI technology should be the tools like this that can augment our capabilities and offer more possibilities. So that related to the reframing of the relations between AI and humans from this algorithm-centric to this human-centric AI. So previously we have this kind of universe where the algorithm and AI is the center. So we try to develop an AI algorithm to improve the numbers and to crush benchmarks. Then the human developers is just surrounding the algorithm. So we want to develop better and more efficient AI algorithm. But the human-centered AI is another design of the universe. So in this universe, then the humans will be at the center, then algorithm will surrounding us. So it's more like we want to develop better and efficient algorithm that can better support our human capabilities. So that is the central ideas of human-centered AI, which I'm very excited about. So when we're talking about the human-centered AI, so there is a very important attribute, the human control versus AI autonomy. Because right now we are developing the algorithm that can automatically doing a lot of things. Then this kind of relation between human control and the AI algorithm become a binary attribute. Sometimes we want to have high human control, then there will be low AI autonomy. And if we want to have high AI autonomy, then we will have low human control. But I think this kind of attributes is not necessarily be binaries. There could be two dimensions to describe this kind of attributes. We can have this two-dimension grid. The horizontal axis is machine autonomy. So we have high autonomy and low autonomy. The vertical axis then will be the human control. So in that case, we can have two dimensions to describe this. So let's say our eventual goal will be building reliable, safe, and trustworthy AI system. So we want to go to the upper right corner. Then we already have some inventions in that direction. So we have, for example, we have the elevator. We also have the digital camera that can provide you a lot of options and configurations. So you can just control the parameters you want. Then you can just click the buttons. Then this elevator can deliver to the floor you want to go, or the camera can take pictures you want. So in that case, we have high machine autonomy as well as high human control. On the other hand, we also have some inventions have no machine autonomy, but high human control. So that's relevant to this bike or piano, right? Humans take a lot of time to practice, and we can master the skills. So in the case, the machines will have low autonomy, but we have a high control over that. Also for this other inventions such as the airbag and the pacemakers, so we have very high machine autonomy, but have no human control. So for example, for this airbag, so when everything normal, then we are not aware of their existence, but if some accident happens, they will be engaged and save our life. Also for pacemakers, we will not feel it at normal time. In the case, they will have high machine autonomy and low level human control. Then we also have this low human control and no machine autonomy, such as music box and the night mice, right? So AI models and the AI applications also should put in this case. So we want to build a more reliable and trustworthy AI system. So that is our goal. So we want to go towards this upper right corner. So, but our current AI system have this intermediate machine autonomy, but have no human control. So we want towards this goal. So we should do both ways. So horizontally, we should put more effort of developing new AI algorithm and the AI models to improve the performance and the machine autonomy. And we also should put the efforts developing this human interactive AI, also improve the human control on that. Then we can move towards a goal. So through this talk, I will talk about the human AI interaction in the field of computer vision and machine autonomy. Like how can we build this reliable and interpretable relations between humans and AI models? I would think about this relation like your relation with your pet. Like, for example, you may have a dog, right? So you have this dog, so you interact with your dog and you walk your dog every day. So that is your AI models. Most of the time, it works quite well. It can listen to your orders and work with you. But sometimes this AI model will doing crazy stuff and refuse to work. Then in the case, you have to put more efforts and you have to babysit your AI models to make it better. So through this talk, I will give you some of the concrete examples. How can we enable such human AI interactions? So I will talk about the image classification model. How can we make it more interpretable? Then we'll talk about image generation. How can we have more human steerable image generation? Lastly, I will talk about this machine autonomy application. How can we build this human in the loop system that can improve the reliability and the safety of the AI system? So I will skip the technical details, so just to give you very high level ideas. So if you are interested, you can check about the papers in more detail. So first part is the image classification. So for image classification, we already have a lot of human AI interaction. So because in image classification, the dominating method is the supervised learning. So in order to do supervised learning, we will have a lot of humans involved in the annotation loop. So we have thousands of humans to annotate data for the AI to learn, right? So we have this kind of interface, so to ask workers to whether this image is eclipsing or not. So this way, we build a lot of different image database. So one of the scene understanding database we built is this places database. So for this places database, we have 50 million images annotated by 5,000 crowdsourcing workers for 1 year. So from those annotations, so we can train some supervised learning algorithm and some neural networks. So here is a scene recognition demos we built. So it's still working, so you can upload the image, then this model can return your prediction. So for example, for this image, I feed into the neural network. So give me the prediction, 72% indoor booth, which is correct. Here's another photo of me, so chilling on the beach. Then giving this image, give me the prediction, 62% beach, which is all right. Right. So here's another photo of my friend. So he's just doing nothing, right? Just sitting on the floor. But when he uploaded this image, then he sent the result to me. Hey, this model is doing some wrong prediction. So this model gives the prediction 95% martial art dream. So we have no ideas why this model give us this prediction. So for sure, my friend is not like Bruce Lee, and he doesn't know any kung fu or something like this. So he just sitting on the floor. So why this model give us this prediction? So we try to understand why. So then that lead to our works that we try to provide the human interpretations to the prediction. So we want to explain this prediction to humans. So that is the motivation behind the method we developed, so which is called the class activation mapping. So it's a very widely used method to interpret the prediction given by the network. So what this method doing is that we look into the internal activation of the neural network. Then we can generate a heat map to highlight the most relevant regions to the prediction. So for this particular example, you can see is actually the bare feet makes this model make this prediction. This is martial art gym. That makes sense because in the martial art gym, people usually want to wear shoes. So this model just pick up this BIOS information to provide this prediction. So this kind of interpretation have been widely developed since very first few works. Like this CAN is developed like more than 6 years ago. So afterwards, a lot of work in this model interpretability and the explainability. So the general idea is also build this human understandable predictions, and then we want to generate some heat map or some explanations for the decision. So here is a nature medicine work from Google. That's they build this kind of interpretations to enable the human AI collaborations for the skin cancer recognition. So towards this live work, so I would like to highlight some of very wonderful textbook or some great book added by Dr. Samik here. So very nice work. So for those audience interested in this model interpretability, so I will suggest you to take a look at this Explainable AI or XX AI beyond Explainable AI. So that give you some overview about recent progress in this Explainable AI for the classification task. So that is the first part for image classification. So how can we build more interpretable relations with the classification model we have? Then let's shift to the second work, is image classification, right? So that is also very exciting areas in computer vision. So we have many amazing generative models that can synthesize realistic images. So here I show you some results generated by the StyleGAN. So it's very realistic person face. So you can clearly see the texture and skins on the people. And also for the nature scenes, we have the very realistic the object compositions and the lighting conditions. Also recently we have this people generation model, also DALL-E 2, that can generate images from sentences. So for all the image generation models, so they generate something out of the random vectors. For this generative model, so the inputs is usually some random vector, then the outputs are those diverse images. So this model are fine, they can generate very realistic images, but what we human care about is how we use the generative models to edit and create, right? So that's what we care about. Not just those models just generate a lot of fake images. What we care about is to use this generative AI to do some photo editing or do some creations. So then that lead to the application of AI assisted content creation, right? So we wonder about how can we use the AI generative model to edit our own image. So here is one a photo of mine. So let's say I want to try different styles. So here are a lot of Hollywood celebrities. Then I want to try if I change hairstyle like theirs and how I should look like. So we develop some method that can do the scan inversion, like invert my face into the latent space. Then we can do some optimizations. Then I can try my styles try my face on different styles. So I really like this kind of long hairs. So seems I should start growing my hair. So those kind of application allow people to edit their own images and photos. So we develop many methods such as interface scan or GAN stability and high GAN CFAR method that try to do this latent image editing. So for this generative model, we have some latent space. So we have this work that try to interpret the latent space. Then we can guide this image generation process. Then we have this human steerable image generation. Then we can control this generation process. Like for this particular generated sample, we can make it looking older. So we can change a lot of different attributes. So here is another CVPR work we have done last year. So we developed some methods that can discover the meaningful hidden factors inside the generative model. So let's say this model give me a cat. Sometimes we are not so happy about output, then we want to change different attributes of the output image. So we developed this method that can automatically identify controllable factors inside the model. So on the left side panel, so each slider bar corresponds to some attributes. So we can change various attributes of our image, such as texture of the cat, or even for this cartoon characters, we can some dimensions align with the pose of the person, like the side of the mouse. So we allow user to involve in this content creation process. So they can edit different attributes. So we also have some recent CVPR work that try to increase the spatial control of the image generation. So like for recent work, the DALL-E 2, so it can generate image out of a sentence, but sometimes the location of the object is not that ideal. For example, for this cat, we may want another image, want this cat head move up a little bit, or we want this head move right a little bit. So for this kind of spatial control, so current method doesn't support that. And therefore, we develop some method that try to enforce some spatial key points in the generator. So we develop some method self-supervision of spatial key points in the generator. So what we are doing is that we design some spatial inductive bias into the generator, then utilize the discriminator of this models. Basically, this discriminator you can consider as a classification model. So we can use this attention map to pull out this self-attention heat map from this discriminator and use the heat map as a supervision to the spatial inductive bias. So we have this kind of self-supervision, and we can train this spatial inductive bias. So after the trainings, then we can have this spatial key points. So here is the demo video showing you that user can just drag this spatial point, then we can regenerate the image. So in that case, then we can control the location of some of the content. This kind of spatial points also happen at different levels. So we have this intermediate levels. The user can just drag this spatial point. Then we can change different attributes. Like here is at the fine-grained levels. Then we can control more fine-grained detail, like the size of the ears for the cat. So here's another demo videos on this buildings. So we have this the key points. Then user can drag this key points. Then we can move the contents over this map. So the side of the towers So here at the intermediate levels, then we can control the button building styles. Also more fine-grained levels, very subtle movements for the style, like location of the windows and the doors. So this method allows users to have more fine-grained level control on the generation process. So we can change the spatial locations of the contents. So user can play with the demos and create the image they want. Okay, so that is a second application. So I show you that we can vary some inductive bias in the generator, then we can make this generation more human controllable and steerable. So we can have this reliable interaction between the generative AI and the human. The last part will be more on the machine autonomy. So how can humans in the loop to improve the safety and the reliability of both the learning and the inference, right? So one of the popular machine autonomy algorithm is this reinforcement learning algorithm. So it's an algorithm used in this AlphaGo and also the Atari deep Q learning. So it's widely used in this machine autonomy. So some people use this for learning to drive. So this algorithm is just the interaction between agent and the environment. But the issue for reinforcement learning is that they don't have any safety guarantees for the agent. So here is a video showing you this learning process. So during the learning, this agent have to try a lot of crazy behaviors in order to pick up the correct behavior. So you can, this agent learning during the learning process, doing a lot of crazy driving behaviors, scratch other cars and running into the traffic cone. So cause a lot of trouble in order to learn the correct behaviors. For this kind of learning process, so it's not so scalable to the real world deployment, right? So it cannot ensure the safety, then we cannot use this method in real world. So in a case, we want to improve the safety of the learning process. So what we explore is introduce human into this interactive learning process. So besides the interaction between agents and the environment, we also have the human in the loop. So we want to improve the learning process. So in the case, the human subject will play the important role for safeguarding. So it will guide the active exploration of the learners. It will also demonstrate the correct action to the agent when this agent running into some trouble, right? So we developed some method called human AI copilot optimization. So in this case, so we have this experts in the learning process of the agent and the environment. So it will take a look at the state and check whether they will lead to the safe behaviors. Then if some risk situation will happen, then we'll take over and show the correct action. So here are some technical detail. So I just ignore here. So develop some algorithm called the human AI copilot optimization. So it leverage some intervention minimization, and we can train our policy. So it's published at ICOR this year. So you are interested, you are welcome to take a look at the papers. So here I show you this demo video. So here I show you a demo video. It's just showing you the whole learning process. So in this learning, so we have human subject in the loop. So this human subject will monitor this learning process. At the beginning of the learning, so this agent cannot do anything. So there will be more like imitation learning. So the human will do all the demonstration to the agent. So the agent will learn from the human demonstration. So you can see after 6 minutes of training, this agent already learned how to drive in the straight road in the simulation environment. Then you will notice there is a corner coming. This agent still have difficulties to turning around the corner. Then there will be the human intervention to show this agent how to drive around the corner. So you can see after about 10 minutes of this interactive learning, this agent already know how to drive in this empty town. So it's a relatively easy driving task, but you can see this algorithm is very efficient and know how to drive in this empty town in just less than 10 minutes. So driving behavior also human-like, because we have this human interactive demonstrations that can pick up the correct driving behaviors in this. Okay, so that is the work on this human in the loop learning process. It's just in the learning, human will help the agent to learn. Next, I will talk a little bit on a very recent work that we try to improve, try to enable the human AI shared control. So it's more like we in the inference or in the testing time, how can we put human in the loop of the inference? So that is very important for managing this human AI teaming, like human can how the robots can team up with humans to accomplish some task. So here is one toy example. So this autonomous agent just trained from reinforcement learning. So it just trained to accomplish the primal task. So the primal task for the agent just to move forward. Then this agent can just move forward, right? Just doing this repeatedly, doing this very boring behaviors. But there are many fundamental questions remains. So how can we humans control this trained agent? Like for this, after you training, right, this agent can just execute the behaviors in the environment. Then there is no way for human to like issue orders. You should turn left, you should turn right. So there is no way human can control this agent. It's also relevant to the interpretability of the reinforcement learning agent. So what has been learned inside this interactive agent. So we have a very recent work called policy dissection. So it's a work that derived from our previous work on network dissection and the GAN dissection. So we're looking to this reinforcement learning agent and try to understand what have been learned inside internal representations. So this work just accepted to NeurIPS. So we'll present this work at the NeurIPS this December. So what we are doing is that we try to analyze the relations between the internal representations and its agent's behavior. So this policy dissection starts with policy rollouts. So we'll do a lot of rollouts. Then we can collect a lot of behaviors. Then we can collect a lot of kinematic attributes. We also can collect their internal activation, right? So those activation, the kinematic attributes are more like some time series. So right now we want to build the correlations or even calculate the causality between the two. Then we perform some frequency analysis. So it's some time series analysis methods. Then we can associate some attributes, kinematic attributes with the internal representations. So we can identify like which regions, internal representations associate which attributes. And then after we interpret that, then we can build some, so we can have this human interface, and then human can activate and deactivate certain regions. We can evoke certain behaviors such as deacceleration and or move up. So here is the results. So we apply this policy dissection, then we can identify the meaningful regions that we can associate those interpretable regions with the keyboard. Then user can simply press the certain keys. Then we can evoke the behavior of this agent. So here is a demo video showing you that user can press certain keys. So we can issue order to this agent, like move left, Also press move forward or stop there, and also doing spinning around. So user can simply press a key, then we will activate and deactivate the region. So you can think about this as more like a neuroscience approach, like EEG approach to some intelligent animal, right? So neuroscientists study these animals like mice. They will put some spike into the brain that will activate those certain regions and will evoke certain behavior. So we are doing this kind of AI neuroscience. So here's another result is a lagged robot. So this robot, before training, they just cannot. So this training for this agent just doing this move forward. So it can accomplish this task by training from some reinforcement learning algorithm, the PPO. But after training, we deploy into some new environment with some obstacles, then the agent cannot navigate. Then we apply our quality dissection to the agent. Then we can enable this kind of interpretable interactions. Then user can press the keys. Then it can work with this robot, then accomplish this navigation task. So you can see there are many obstacles. Then user can issue some order, like whether you should turn left, you should turn right. Then it can safely navigate through this environment. Although this agent is not trained in this testing environment. So why we say it's more like test time generalization through human AI control. So here's another result. We further apply this quality dissection to this Cassie robot. So this Cassie robot is a robot, is a bipedal robot. So we just train this Cassie robot to move forward. Then we apply our policy dissection to this training agent. Then we can discover various skills inside the model. For example, now many different skills can be discovered, such as crunch, like even backflip behaviors can be discovered. So we can combine those discover skills into this parkour environment. In this testing time environment, you can see it's very complicated. There are many obstacles, many barriers. So right now, so human will work with the agent to do this task. So they will press the keys and it's more like issue high-level order to the agent. The agent will execute this low-level things. You can see there is a bar coming, then we'll order the crouch behaviors to the agent, then you can pass this force. We also can evoke this like backflip. So you can think about this backflip behavior as more like have a vertical jumping and horizontal force. Then we'll evoke these two behavior into the agent. Then we can control, evoke this backflip behaviors from the agent. So this kind of human AI shared control is a direction I'm very excited about. So you can think about these future applications, like those autonomous robots. So it will not like replace human. It's more like we have this human AI hybrid system. Like we human will be more like a commander. We will issue the order to those robots, and the order, and then those robot will execute those low-level behavior, and will always listen to our orders. Okay, so here is a summary on this. So we want to enable the human AI interaction in this computer vision and the machine autonomy. So I already show you many different applications, from image classification to image generation to recent machine autonomy. So ultimately the goal is to create the synergy between the machine and the human intelligence. So we want to use machine intelligence to augment and amplify our human intelligence and capabilities. So there are many applications I talk about today, from this human steerable image generation to human guided learning to human AI shared control. So I'm very excited about these directions. So I hope you can take a look at this human-AI interaction. So all the papers and the works I talk about today are available at my homepage. So I'm very happy to answer any questions you may have and engage with the audience. Thank you.
Yeah, thank you very much, Bolei, for this great talk. I'm sure we will have lots of questions from the audience. With one. What about, like, I very much like the idea of like human interacting with AI, also like human, yeah, like supervising or giving some hints to AI. What about changing behavior? So can we use a human to, for example, adapt more quickly? So for instance, in autonomous driving, if your model is trained to ride on the to drive on the right side of the street, and now you go to UK, you have to drive on the left side, or maybe some meaning of some traffic signs changes or different in different countries. So can you use the human to help the model to adapt more quickly, or do you need to retrain, like, or with very much of examples?
Yeah, that's a good, very good question. So there are two sides on this. So one is whether we can use humans to improve the AI. So I think it's possible because we already showed that the AI representations learn many rules and common knowledge from the environment. Then we can interpret those knowledge inside the representations. Then we can easily like rewrite or overwrite those rules and replace with the rules we want. Another side is application about whether we can use AI to help humans. Like if I travel to UK, then drive on the other side, I'm used to driving in US. Now whether this AI, this autonomous driving vehicles can help me learn faster. So that's related to the interaction between human and AI, whether we can use AI to improve human capabilities. So I think it's possible, but it's also less explored directions. Especially we have more and more superhuman AI models, then of course we should use the superhuman AI models to improve human skills.
Mm-hmm. And like, so and can we like only interpret afterwards and do it like during the deployment, or can we also like use the human to guide the training process to make things like, I think you showed some examples, but I just maybe want your opinion about how can we integrate prior knowledge, things that we know, into training, into guiding the model.
Yeah. So in our work, so we just have this interaction between agent and environments. Then we have human as a third party into this learning loop. So that is one way to incorporate human knowledge, because the agent actually learn from human demonstrations. With human demonstration is more about how human will do the things, then the idea or intent will be conveyed to the agents through this human demonstration. But there are many other ways to convey human intentions, such as we may use some language model to encode the sentences, then we can convey the representation to the agent. We also can use a human preference, like ask the agent to do some behaviors. Then human will be the judge and see this behavior is 90% correct, this behavior is 10% correct, so I prefer this behavior. So there are multiple ways to convey this preference to the agent. Also, it's related to this kind of how can we embed the symbolic knowledge into this. I think that is a field for this like deep symbolic learning. And how can we combine the symbolic learning with deep learning? So that is, of course, very important directions.
Yes, I think, I mean, it's also some possibilities or opportunities for like justifying AI, because if you can make sure that your AI behaves in a certain way, like a human, for example, I think this would be really a step forward, because when it comes like to making sure that your AI is trustworthy, people in the past always said, okay, it's a black box, we cannot understand what's doing. Maybe it has learned to use some stupid correlations in the data, or some artifacts in the data. And I think this is really like a step forward if we can like ensure that the behavior of your model is to some extent similar to what a human would do. Or what do you think about that?
Yeah, that's you touch upon another very important direction or point, research direction, is that sometimes human intention or human desire for the agent cannot be expressed into some loss function or some reward function. Like for image classification, the objective is easy to define, but for like driving, like you want to reach the destination faster, or you want to reach the destination in a safe and reliable way. So it's very difficult to define the reward function, because we have some work that try to develop some environments. So for this reinforcement learning environments, we have to define the reward function. But we realize it's very difficult to define this reward function. So this kind of human demonstration is a good way to overcome that. So we don't have to define a scalar reward function. So we can just use a human demonstration, interactive demonstration, to correct the agent's behavior. Then the agent will say, oh, I'm doing this kind of behavior. That human wants to intervene my learning, then that should be good behavior. So that's more like we convey our intention to the agents in this implicit way. Then the agent can better understand what is desired. That's also related to this AI alignment topic in this AI ethics and trustworthy AI. Like how can we align the human intent with the learning objective of the agents? So that it will have a lot of work to be done, I think.
Mm-hmm. So we have a question from the audience, like how do these wonderful capabilities contribute to good, or how can we prevent actors from creating harm? And are you working on some applications of AI which have like some, I don't know, social impact or some kind of impact like beyond this image domain?
Mm-hmm. Yeah, I think it's really domain dependent. Not many like AI ethics things, like you predict the skin of the person, or doing this like CV, like resume screening. So there are a lot of this bias and bias in the model and bias in the data. So we need to dive deep into that. So I think that's a very important issues. So one very important thing to do is invite this domain expert, like for domain experts to sit together with the AI developers and to analyze the problem together. Like we have some work, a collaboration with this UCLA healthcare. Like UCLA have very strong medical school, so we have to collaborate and talk to the human doctor, like radiologist, and check this AI models, and they give us very interesting feedbacks and see how they will use AI models and what questions they have about the AI decision. So that will involve this domain experts with AI experts, and we can jointly develop this technology. So that's so it's very important to have both parties involved.
Mm-hmm. So do we have other questions from the audience, from the neural network? Then maybe I have still one. So you presented like this approach for the image generation or with the GAN. So is it only applicable to GAN, or also like to other types of generative models, like diffusion models? Or what is maybe your opinion also, like comparing like GAN with other types of models which have become very popular nowadays?
Yeah, that's a good question. So the diffusion model is more like a hurricane that's taking over all the generative model, just overtake the GAN. Then everyone's attention focused on the diffusion model. Yeah, it's a very exciting area, especially like past few weeks, like past week, and many new works on the diffusion model. So I think that is a change, because these companies, Google, Facebook, they have a lot of computations that can train this diffusion model. Then like OpenAI also train this study too. So this model, after you have this large scale model. They learn from this massive number of data, then they can generate realistic images from sentences. So that's a very exciting area. So I think, but there's still many issues to overcome. Like when this OpenAI like open their API to all the general public, then when designers using the models, there are many issues. This model right now can only like doing the sentence, like generate the image from sentences, but sometimes the generated images are not, people are not satisfied with outputs. Then they have to do this prompt engineering, like change this wordings about sentence. Then that's a very inefficient way to guide the generation process. I think a better way is to have more like maybe human can like sketch something, then feed this draft to the AI model, then can generate things human want. So I think current diffusion model should have more human control on it. Not only using the sentence to control it, should have multiple level of control. Like we have the spatial control or many other control way to let user convene their ideas. So there should be many work to be done when people start like deploy this model to general public. So I'm looking forward to what they can do.
Mm-hmm. So I don't see other questions. So then I would like to ask you a last one from my side. So what do you think is the future of the field of explainable AI? Do we like move towards like, do also explanations need to be more interactive with the humans? So what are your opinions on the next steps?
Yeah, I think explainable AI will be like one topic under this human AI interaction or human-centered AI interaction, because we want to make this AI more interpretable. So there are many other related topics I'm very excited about, like for when you apply this explainable AI to generative model, then depending on the tasks, then you can have this human collaborative content creation. So make the generative AI more interpretable and more controllable. Then you have this interactive content creation. So we also have the last work showing when you apply this expandable AI to this machine autonomy, then you can have very nice application of this human AI shared control. Like a human can work with AI to accomplish some tasks. So those are the direction I'm pretty excited about. So it's more like try to open the doors, not limited to the classification-based model. So I agree that there's still a lot of work to be done to provide explanation for the classification-based model. But the eventual goal will be how human can work with this model to accomplish human tasks, right? It's not just generate explanation for explanation purpose. So we want to generate the explanations then to enable human experts to work with the AI model to accomplish their task. So that is a direction I think worth going.
Yeah, I fully agree with you, Bolei, and especially on this topic. This is also where we are kind of heading to. And yeah, it was a pleasure. Thank you for this very nice discussion and also the very informative presentation. And hope to see you soon, at latest next year at UCLA.
Yeah, sure.
Bye-bye.
We're happy to chat with you in person. Okay, thank you for attending today.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. After the networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.